So this is day 2. So day 2, again, we split into 2 sessions. This morning, I'm going to talk a little bit more about using tellurium and Roadrunner, and we'll talk a little bit about kinetics, and we'll do quite a few demos, show you how things work. And then later on, I think am I right, Veronica, that Joe Hellerstein will start talking about parameter estimation? Veronica?
Yep.
Yeah, okay, good. All right, okay, so let's start then. So let me go into view mode. So slides, here we go. Okay, so this is on day 2, session 1. So first thing I want to just briefly go over again the way tellurium and Roadrunner work. So Roadrunner, as we said yesterday, is the simulation engine, and then tellurium is this thing on top that makes it easier to use. So tellurium adds a few extra things like load A, which you saw yesterday for loading the models. It also has a couple of other things like plotArray, which I'll mention today. Then all the simulation methods are in Roadrunner itself. Okay, so that's the actual simulator. And all these images you have on the left, you can use this from any of these platforms, right? Whether it's Jupyter, Colab, Spyder, PyCharm, Visual Studio Code, Anaconda. You can, of course, you can use Python from whatever IDE you want, and of course, this works on all platforms, including Linux. The other thing to emphasize is that because we support SBML, which you briefly heard about yesterday, this is the standard format for exchanging biochemical models. You're not stuck with tellurium or Roadrunner. You can move your models from different tools. For example, Copasi is a popular one. If you like a GUI tool, you can move back and forth between any tool that supports SBML. The advantage of SBML is, of course, tools don't last forever, right? Maybe they have a lifetime of maybe 10, 15 years, and then new tools emerge. The idea of SBML is that your models will still be usable in the new tools, so long as they are SBML compliant. And in fact, I have models from 2002, 2003, which I can still run today, even though that's almost 20 years ago. Okay, so one thing I want to first mention is help again, and I want to show you a couple of things which is probably spotted yesterday when we were using it, but let me go to today's Colab website. So this is the Jupyter notebook I'm going to use this morning. So first thing I did just before you came on, I installed tellurium. And usually when you exit Colab, it sort of wipes everything. And so when you start a new session, say, a couple of days later or a week later, you have to reinstall whatever packages you were using. Okay, so I just went ahead and did a pip install. So pip is the standard way for installing packages, and often from a Python environment, if you want to install it in the Python within the Python environment, you usually have to put this exclamation mark in front. That's not always the case, but at least in Colab you have to. So pip install, then the package name, and -q. -q just means stay quiet, because it can, if you don't do -q, it'll produce a lot of text which you may not or may not want to see. So -q just keeps the output to a minimum, and these are all the packages it's installing, okay, as it installs. So let me import tellurium. So the first thing, of course, we have to do, as we did yesterday, is import tellurium. You see, it's very easy to misspell tellurium as TE, which is why we always shorten it to TE. Now, let's say I wanted some help on something. You notice immediately a little thing popped up. I didn't do anything. I just typed TE full stop, and all this stuff came up. So let's pick, I know I want to do load something, and there's load A, okay? Now, if I put a question mark there, I'll get some help on it, okay? So that's the first thing you can do. So it says load a model from an antimony string, and there's an example. In fact, let's grab this example, shall we? And let's just put it in, okay? So I'll put it in here. So what I'm doing here, then I'm using load A, and inside load A I have a string. This is a very simple model. S1 goes to S2. The rate law is K1 times S2. Initialize K1, initialize S1, initialize S2, and that's it. And then it returns what's called an instance or an object of the simulation engine. So let's run that. Okay, and then I can run a simulation just to show you this working again. Simulate. Let's say I don't know what the arguments are. Something immediately pops up to help you. Okay, so it's start, end, points. So when you see none, that means it's optional. Okay, actually, if you see an equal sign like that, argument equals something, it's optional. In fact, if I do nothing, it does actually return. And if I look at M, you'll see it's data. And the default is to produce, I think, about 100 points, and it goes up to time equals 5 from 0. Okay. Of course, I can immediately plot that if I want. Oops, r.plot. And again, if I just hit the brackets, hopefully, okay, it didn't come up that time for some reason. Oh, there it goes. Comes up with some extra help. And if I could do question mark, I get a whole lot of more help. Okay. Now, Jupyter Notebooks doesn't render the help very nicely. You can see here it's a little bit of a mess. That's a Jupyter Notebook issue. I'll show you something else in a minute. Anyway, let's just plot this to show you what it looks like, and there's the plot. Okay. Now, obviously, you can see that this stuff's still happening after time 5. So maybe I will actually extend it to 40 time units, and then I'll run that. And okay, that may be a bit better. Okay. So that's basically help in the Jupyter Notebooks. What I'm going to show you now is Spyder, to show you what Spyder looks like. So this is an IDE I happen to use a lot of. So are you seeing Spyder here now?
Yes.
Yeah. Okay, good. So let me just do a CLS here to clear it off. Okay. So what I like about Spyder is it's not a Jupyter Notebook at all, or does some. Yeah, it's not at all. But what I like about it, it has an edit window where I can just type in scripts. And of course, it has tabs, so I can have as many as I want along here. And then down here, I have the console, so I can actually type, it's interactive, okay? So I can type things at the console. And then this upper panel has other stuff like help, a variable explorer, plots if you've made any plots, and a file viewer, okay? So it's quite handy. So I can type in stuff here. Do I have the? Oh yeah, I have the previous model there. So let me use that. Okay, and then I'll do the same here. So if I do that, I get basically the same plots I had in Jupyter Notebooks. Now help works in the same way actually. If I go r.sim, actually go simulate, and then hit brackets, I would get the same help. Okay. Alternatively, I can also go question mark, and I get help as well. Again, it looks a bit messy. So instead, for example, in Spyder, they try to, there's an extra facility called Control I. So if I go, oops, hold on. If I go Control I, it'll actually render it in a much neater way. Okay, so each IDE has slightly different helps, but they all pretty much have they have slightly different ways of rendering help, but they all have the question mark facility. Spyder has the Control I functionality. They can all bring up some help on the arguments when you hit the bracket. And if you do r dot, now you notice in this case, nothing has happened. So in the Jupyter Notebooks, you'd get immediately a help here. But in Spyder and most of others IDEs, you don't see anything. What you have to do to get that to happen is hit the tab key. If you hit the tab key, then you get a whole load of stuff. Okay, then I can go, and then I can narrow down. And if I do LA, I can see there's a couple of loads on that, even in the Roadrunner one. But I can do TEL tab, and I get all the L's. Okay, so there's a lot of help, and these pop-up things are really useful because often you can't remember what the name of some function is. For example, let's say I wanted to get a list of all the parameters. Okay, names of all the parameters. So I would go r dot from the model, right? So r dot get something. And I know SBML has this idea of global parameters. So it's probably global something. Oh, there it is. So there's 3 there. So global parameter IDs. So all I have to do is select, hit return, and I get, there's only one course parameter here. The other one was get values. That just gives me the values. Okay. So I just want to show you what the Spyder looks like. This is basically what it looks like. Everybody has their own preferences for what environment they want to work in. I happen to work in Spyder. Other people work in Jupyter notebooks like this, and other people work in PyCharm, other people work in Visual Studio Code, and so on. But whatever Python you generate, it's all course compatible right across all these platforms. Let me just do the same thing I did here in getting the global parameters. So you see that pops up. If I type a G, I narrow it down, and it is the first thing, get global parameters IDs. If I want to know a bit more about it, I just put a question mark there, and I'll get a bit more about information on it. But I don't want any more. I just want to hit return, so shift return, and I get the parameters. So there's a lot of help built in. Okay, so, and if you're stuck, of course, there is the documentation, right? The tellurium documentation, and you can. There's various sections here which I briefly mentioned yesterday, but one in particular is the antimony reference. Okay, so this tells you all about antimony. For example, compartments. I briefly mentioned compartments yesterday. So if I click on compartments, I can see here now how to declare a compartment. So here, for example, I hope the font isn't too small, but it's declaring 2 compartments, cytoplasm and mitochondria, with those 2 volumes. And then it's saying that S2 is in the cytoplasm, S3 is in the cytoplasm, S1 is in the mitochondria. Okay. So the antimony documentation is really useful. There's a lot of stuff here. Okay, lots and lots of stuff. And there's specific Roadrunner documentation that drills down to specific Roadrunner ones. For example, we've grouped it by functionality. So let's say, simulation and integration. Okay, so it gives you some aspects about the simulation tool, the simulation systems we use. Then you can go next, and it goes on to the next topic. Okay, so there's quite a few. There's a lot of material here on, and because there's a separate tutorial again, completely separate tutorial to running Roadrunner itself. So there's a lot of material. Okay, let's go back to the deck. All right, so that's the help. We did that briefly, hitting the question mark. We did that again, a bit more help. And there's also then the cheat sheets, which I mentioned yesterday, which might be useful to you, to give you a quick idea of what to do. And that's it on the help, okay? So I'm not going to say anything more on the help. So if there's any questions, let me know. Oh, there's some chat stuff. Okay, there's some questions on there, so somebody can answer those. Okay. So some little bit review of what we did yesterday. Really the one that you'll use mostly, I guess, is setting and getting values. So if there's a model, the parameters and the species names appear automatically in the Roadrunner object. So you can just go, if there's a parameter called K1 in your model, you can just go r.k1, and you can either look at it or you can assign to it. Same goes for species levels, and of course you can use them just like they're in any expression. So here I'm adding 0.1 to S1 and then assigning the new value to S1. Okay, so you can use these symbols like they're just normal variables. All right, so this is a very useful thing to know. So here's some useful commands which I thought I'd go over. So some of these load A for loading the model, simulate you've seen, plot you've seen, steady state we'll come to later on. But there are things like floating species boundary and so on. So let me let me show you some of these then, right? So I'm going to move this over to here. And then I'm going to go to here. So let's see what some of these methods do then. Okay, so we've seen r.plot. The get, oops, where am I? You've seen the get global parameter IDs, get the floating species oops, not concentration, sorry, get species IDs. S1 and S2, you're often asking for, what are the names of things, or you want to know what are the names of the reactions. So you can do the same thing here. Oops, right? You get J1. So I didn't name this reaction up here. As you notice here, it's just S1 to S2. I didn't name it, and therefore it gives a default name of underscore J0. I could name it something, reaction 1. Okay. Note the colon that separates the reaction name from that. And then I can ask for the reaction IDs, and then I'll get reaction 1. Okay. In terms of values, I can get the floating species. Let me see, get the floating species concentrations. Oops, sorry. Concentrations, there it is. And I get the current concentrations of 10 and 0. The help system is really useful. I mean, we've made these the names of these methods quite long to keep them descriptive, but then you have the problem, you have to type them in, and they can be quite long. So this is why the help system is so useful, because you don't have to type these long names in, but the long names are there because they're descriptive. So you don't have to, figure out, I wonder what this method does. Well, this one does get floating species concentrations. It should be fairly explanatory. All right. What else we got? We got the get the reaction rates. Oops, sorry. Get the reaction rates. There, I got the reaction rates. And if you want to get the rates of change, get rates of change. I get the rates of change. Okay. Now, one thing maybe wasn't you may have missed yesterday, but it was mentioned. You notice this thing is get floating species concentrations. So these are they're called floating because these are the ones that will move, in time as the system evolves. Now there's another kind of floating species, which is the boundary species. And so I'm going to construct a new model here. So let's just construct a new model. Oops, sorry. All right, so construct a new, it's going to be a multi-line model, so I have to use triple quotes if I want to do a multi-line string. So let's set one up, shall we? So it's going to be really simple. I'll probably just have we'll have three steps, okay? And then S3. Now I don't care where S3 goes, so I'm just going to leave it there like that, and then at S3, okay? And then I'll initialize them. I'll just put some random numbers in here. Doesn't matter what they are. Okay, and then I'll set up S1 to something 10, okay? So there's my model, all right? So now I'll do simulation. Oops, simulate, thank you. Let's go to 60, let's have 100 points. So that's the simulation, then plot it. Okay. What you see here is the evolution of S1, S2, and S3. You see S1 starts at 10. Right, there it is, because that's initialized at 10. And then S2 rises and falls off, and S3 rises and falls off, okay? And everything eventually drains out completely from the pathway, because everything just drains out to S3 and it goes off to who knows where, okay? Because I haven't actually specified where it goes. So now, these are all floating species, okay? So if I go get floating species, where are they? Where are the IDs? Oh, here we go. Okay, that'll do. S1, S2, and S3. So there's 3 floating species. Now, if I wanted for some reason to fix one of these, right? I want the S1 in particular not to change at all during the simulation. All I have to do is put $1 in front and it fixes it. Okay, you can also use the external. You can declare S1 as external as well, and that basically does the same thing. All right. Now, if I run this, remember you have to run the cells again. Okay, each cell. I get a completely different behavior. Notice also now there's only 2 lines plotted. In fact, if I run the get the IDs, there's only 2 IDs, S2 and S3. In fact, there is another set of IDs now, the boundary species IDs. Here we go. S1. So these things that are fixed, like S1, are called the boundary species because they're at the edge of the pathway and we are fixing them. In fact, we could do whatever we wanted with them, actually. We can inject sine waves into them and so on. But in this case, they're just fixed. All it means to the simulator is that it doesn't generate a differential equation for any species that's external. Okay, so in this case, S1 here is a boundary species. All right. So in a given part, in a large model, like say an E. coli metabolic model, you may have lots of boundary species. You may have glucose, CO2, you may have lactate, you may have or oxygen, you may have all sorts of things that are at the boundaries of the pathway that are fixed. Okay. Now you notice that if I didn't fix it, right, I got this effect where everything just drained out and there's nothing left. If I inspect the flux through, and I happen to know that the flux is J0, the default. If I happen to look at the reaction rate of the first step, it's actually pretty close to 0. If I run it, let me name this so it looks a bit better, J1. And let me run this up to 600, okay? So let's run each of these cells. It's like I'm running it up to 600 now, so there's a lot of all the changes happen at the beginning. If I now ask for the reaction rate through J0, oops, what did I call it? J1, sorry. J1, it's 10 to the minus 16. It's pretty much 0. Okay, so this, if this were your model of a cell, I would argue that this cell is probably dead. And the reason it's dead is because you didn't have any fixed boundaries to keep the thing alive, right? Because this little mini cell we have here, I'll just put $1 in there, is consuming S1. It's like us consuming oxygen in the atmosphere. The oxygen doesn't really run out. And so now we're at steady. Now we're at what's called steady state. And look, the flux is now 1.0. Okay. All right. So let's return to the slide deck. So those are some useful methods. So there's a bunch of methods for getting IDs, right? Get floating species IDs, get boundary species IDs, get reaction IDs. There's also get compartment IDs, and there's get global parameter IDs. All right. So often you want to look at the names of things, or for some reason get hold of the names. And then there are various things for getting hold of values, like getting the rates of change, getting reaction rates, and so on. Okay. All right, I'm going to jump over that. Actually, no, I won't actually. So let's we have a little utilities package called TE utils, which has some interesting things in it, and which I shall demonstrate later. But I'll show you a couple of things now. So let me go back to the Jupyter notebook. Here we go. So in order to install something, I have to use pip. Oops, pip install TE utils. Okay. I'm not going to bother with the -Q. It's just, this is what you get if you don't use the -Q switch. You get lots and lots and lots of text. It looks very impressive, but it's useful for debugging. But normally you would just use the -Q. Okay, so if I go import TE utils, these are sort of grown over time, these utilities. So I've called it TU. Okay, so if I go TU, you see there's a whole bunch of things. There's some extra plotting methods. There's some things for doing pretty tabular things. But what I'm showing you here is what you can build for test purposes. You can build random networks. Okay, so I'm going to build a random network, and it takes a number of species, let's say 10 species and 14 reactions. Okay, and I'll put this into, I'll call it network. Okay. So if I print network, I get this random. This is just a random network it's made. Okay, so useful for testing purposes. So what I can do now is I can actually load this now into Roadrunner. So load a network. Oops, what happened there? There it is. Okay, and then let's do a simulation. Simulate. Now I have no idea what I need here, so I'll just put in, so I'll put in 200 points, and then I can r.plot. Who knows? So this is going to be the surprise. What is this random network going to do? It could go crazy, or it could do something normal. Let's see what it does. Now it looks pretty normal. Okay, so sometimes when you generate these random networks, some species just go off to infinity or some crazy stuff because it's just random. But anyway, this one has gone and done that. Now this one, I can now get floating species IDs. You'll see there's a lot more of them. Oops. All right, there's a whole bunch of them. If you want to know how many, you can either just get the length of that list, or you can get num. There's a whole bunch of get nums. Right, so I can get the number of floating species, and it says there's 8. How many boundary species were there? Let's see, 2. Okay, so you can do all sorts of things like that. So if you want random networks to test things out, TUtils has this build network thing. Now it's a fairly basic random network generator. So Michael Koshin in our group has released the papers under is being resubmitted, revision has been resubmitted, called SBBadger, which is a much more extensive package for generating random networks, because it also does, you can also set the frequencies of the node, the connections to the nodes, and in fact you can make networks look more like actually real biological networks statistically. So it's actually more a research level package if you want to test any new algorithms on, so it's called SBBadger. If you want to test new algorithms on networks that look sort of that are synthetic but have the properties of real networks. Okay, but for quick ones you can just use build networks, but for more sophisticated stuff you should use SBBadger. Okay.
Robert?
Yeah.
Quick interjection. When you're done with your session, would you mind downloading all of these live notebooks to upload to? Okay, thank you.
Yes. In fact, we had the same request last time as well, last year. Okay, let's see. All right. Okay, so my slides tell me do a demo on the help and install packages. You've done that. Okay, so let's move to some theory then. So we'll have 10 slides of theory, and then maybe I'll let you do something. So we can't really avoid it, but enzyme kinetics is one of the core topics in any biochemical simulation. Unfortunately, it's not taught so much these days, at least in the US, as much as it used to, and so it's a sort of it's not something that people know too much about anymore. So I thought I'd go through some topics on enzyme kinetics. So you all know what an enzyme is, presumably. So what you may not know was the first enzyme discovered was sucrase. Can't remember the date now, but over 100 years ago, I think. And sucrase takes sucrose and splits it up into glucose and fructose. Okay, that was the first enzyme that was discovered. Since then, thousands upon thousands of enzymes, of course, have been discovered, and their structures have been determined. The question is, right, how do you describe the rate of reaction for an enzyme? Right, how do I describe how the rate of glucose production is a function of sucrose? Right. And the heyday for that kind of work was in the 50s and 60s. And a whole field was developed called enzyme kinetics. And I want to briefly cover some of the basic enzyme kinetic rate laws that you might want to use. So yesterday we came across mass action kinetics. Oops, that's the wrong one, sorry. Mass action kinetics. So that's really simple. That's where the rate of reaction is proportional to the concentration of a species. All right. If there are stoichiometries involved, then you raise the concentration to the stoichiometry. That's what this is. And this is a completely generalized one here. So it's got any number of reactants and any number of products. Okay, and it's reversible as well. Note the minus sign there. What I want to first talk about are these Michaelis-Menten type kinetics, because this is probably one of the workhorses for a lot of your models, some kind of Michaelis-Menten rate law. So let's talk briefly about that. So in the textbooks, you'll probably see these kinds of things shown. So the top one in green, this is the classic mechanism for enzyme mechanism. So you have enzyme plus substrate gives the complex, and that breaks up into free enzyme plus product. This is the one you usually see. In reality, what happens is the one below, where actually product can hop back on. I mean, if the product can come off, it can go back on again as well. Hops back onto the enzyme, forming the complex. And in fact, it can even go all the way back and release substrate. So in a real enzyme, in a cell, you usually get some degree of reversibility. Now, some enzymes like triphosphate isomerase are extremely reversible, and they freely go back and forth. Other enzymes like phosphatidylkinase are less reversible, and the chance of product going back to substrate is not as common. So you get these degrees of reversibility. It's difficult to say for sure whether it's difficult to say that a reaction is perfectly irreversible. But sometimes you can sort of say, well, approximately it's irreversible. Now there are ways of dealing with that, which I want to mention, because the product is still there and it's still got the potential of hopping onto the free enzyme and then reducing the rate. So remember that if product hops back onto the enzyme, it sequesters some of the free enzyme, and therefore there's less free enzyme for the substrate to bind to. And that means that product can slow down a reaction, right? So we can easily construct, and one of the exercises later on, you'll do this. You can easily construct a model like this in tellurium. Say let's do the top one because it's the easy one. So you'll have just three reactions, and 1, 2, 3, 4 species. Okay. None of these need to be fixed. You can make them all floating. You can set up numbers for K1, K-1, and K2, and then see what happens. If you do that, you see something that looks like this. All right. So this is a simulation for this top mechanism, the irreversible one. Okay. And it shows we start off with some substrate at 10 in red, no product in black, and then we let it run in time. And you see that there seem to be 3 phases. There's a first initial phase, which happens very, very fast at the beginning. And then there's a middle phase where everything seems to be relatively, the rates of change, the rate of production of product seems to be relatively constant. The rate of consumption of substrate seems to be relatively constant. And the concentration of enzyme substrate complex seems to be relatively constant as well, although it appears to be drifting down a little bit. And then there's a final transition where we run out of substrate and then everything just comes to an end. Okay. Now, this phenomenon was noted early on by researchers, and this middle portion in particular was of interest because it enabled certain approximations to be made, which made the analysis of enzyme reactions much simpler. Okay, so the beginning is very, very fast. You see the transient here is really fast. Everything snaps into what looks like some kind of steady state or equilibrium at the beginning. And then it's only at the end, then everything starts to run out and everything falls apart then. All right, so we can exploit this this effect that we see in the middle here. So why don't we do this? So we can do 2 things. We can assume that ES is relatively constant here because it's in equilibrium with the free enzyme and the substrate. So if you look here, we can say that in the middle portion that that ES and ES are in equilibrium with each other. That's one assumption we can make. The other assumption we can make is that the thing seems to approach some kind of quasi-steady state where ES is relatively constant. So we could say that, yeah, ES is, although S and P are changing, ES appears to be in some sort of, steady state. We call it a quasi-steady state because not all components are at steady state, but ES appears to be pretty steady. And so those are 2 assumptions we can make. And it turns out that doesn't matter which assumption you make, you also always end up with the same result. So let me just go through that. So let's first assume that E binding to S is an equilibrium, all right? So if it's an equilibrium, then the ratio of E times S to ES must be equal to the dissociation constant, okay? So this is just the middle phase of those plots. Now, the other thing I know about this system is that the total amount of enzyme mass in the system is fixed. So there's a fixed amount of enzyme in the system, and it's either in the form of free enzyme or in the form of enzyme substrate complex. So I know that there's a total amount of enzyme, all right? So I can combine both these equations, the KD equation and the ET equation, to solve for ES. And if I do that, I get this equation here. So ES equals ET times S divided by KD plus S, all right? So what this has given me is the concentration of ES during this phase here from about 0.05 up to 0.08-ish, right? That's what it's given me. And if you look back at the mechanism, you'll notice that the rate of production of product is basically proportional to the amount of enzyme substrate complex. So the reaction rate or the production of product is basically equal to K2 times the concentration of enzyme substrate product. So I can go further and I can multiply this by what was it, K2, and I'll end up with the reaction rate. And this you basically end up with this raw. And this one is called the Michaelis-Menten equation. If you have a KD, which is the dissociation constant in the numerator, the denominator, this is the Michaelis-Menten equation. All right. And the VM is called a Vmax. It's basically the enzyme substrate complex. Enzyme substrate complex times K2. Right. Now the other way of doing it is to assume steady state. In other words, and I'm going to let me see. And here, yeah, I'm still only going to do the irreversible one. So forget the K-2. Basically, I'm going to write out the differential equation for how fast DES is changing, and it's this one. There's two ways to make it. There's one way to get rid of it. And then I'm going to set this to 0, right? I'm going to assume DES by DT equals 0 because you're at steady state. And I solve for ES. And if I do that, I get exactly the same equation again. This time, however, the K in the denominator is not the dissociation constant, but it's some function of all the rate constants in the system. And then that's called the Km. Strictly speaking, this is called the Higgs Haldane equation, not the Michaelis-Menten equation, but people don't seem to bother, and they call this the Michaelis-Menten equation as well, because this was derived by Higgs Haldane, Briggs Haldane, but the Km though has got the name the Michaelis constant. So okay, so what kind of behavior does this show then, right? So this only works at the middle portion, right? Oops, sorry, I've jumped up. This equation only works at the middle section. So it doesn't work at the beginning, and it doesn't work at the end, right? Okay. So that's one limitation of it. What kind of behavior does it show? All right. So if I were to plot the reaction rate versus the enzyme concentration at fixed substrate, I get a straight line. So that means if you double the enzyme concentration, the reaction rate will double. All right. The second thing is if I plot the reaction rate versus the substrate concentration, I get this classic hyperbolic curve, which you're probably familiar with. It starts off linearly and then it curves off and eventually saturates as all the free enzyme is used up, is sequestered as enzyme substrate complex. Okay. And we can define the Km here as the value of the substrate concentration that gives you half the Vmax. Okay. All right. Now, this is the irreversible case. Now, this version is great for things like enzyme assays, where you're assuming you don't have any significant amount of product. But in a cell, there is product. Because if there's no product, the next subsequent reaction can't go. So there will be product in all cases. And so you're assuming, if you use this equation, you're assuming that the product has no effect on the reaction rate. And that's not true. So in fact, if you're going to build some kind of metabolic model, I mean, sometimes you can get away with this, right, using the irreversible case, if you know what's going on. But often people do the full reversible one. The full reversible one is more complicated. It's got one forward Vmax, but it's got two KMs, a KM for the substrate and a KM for the product. The other thing it's got is the equilibrium constant, okay, as well. So this is the reversible case, okay? And this is the one you probably should use unless you have other information. Now, if you can't use this one, for some reason, or you don't want to use it, there's actually an alternative to use, which I'll come to in a minute. So what we're going to do now, we're going to do a little demo. To introduce this demo, I'm going to introduce a new function in tellurium called plotArray. And what plotArray does is it takes a NumPy array and it assumes the first column is your x-axis and all other columns that you may have are the y-axis. Okay. This is just a little bit easier than using matplotlib. With matplotlib, you'd have to do, it gets a bit tedious to do multiple plots like that. This one, you just have one big array, it'll plot the whole lot. Okay. So let me do a demo here then. Okay, so I'm going to move this over here and I'm going to go back to this one. So what I'm going to do is I'm going to show you how I can plot the Michaelis-Menten curve. So let's say you have an enzyme, right? Mechanism, you have an enzyme rate law, and you want to know how it behaves. You want to be able to plot this. Okay. But it turns out there's an easy way to do that in tellurium. So let's do this here. So let's build a model. So I'm going to build a model first. Okay, and I'm going to write in a reaction. It's going to be S goes to something. I don't care what it goes to. And I'm going to type in here the Michaelis-Menten equation. Okay. There you go. All right. That's all I've done. And then let's initialize a few things, shall we? So let's say the Vmax is 10, the Km is, let's make it 2, shall we? All right. Now, if I run this, let's set up S to something just to show you what'll happen. Let's run the simulation here. I don't know, let's go up to 10, I guess. Oops, I want to do is put it in the same one. Dot plot. Okay, let's see what this does. Oops, sorry. Let's do that. Okay, get that. That just shows you, the S is being used up over time. It hits 0 eventually. That's not very interesting. What I want is this plot. I want substrate concentration on the x-axis and the reaction rate on the y-axis. But of course, tellurium gives me time on the x-axis. So how can I make the x-axis the substrate concentration? What I can do is I can use time as a proxy for the substrate concentration. So what I can do is I can do this. I can say let the substrate concentration be time. So I'm pretending now that time is the substrate concentration. I'm going to get rid of this because I can't have that there as well. And the other thing I'm going to do is I want to plot the reaction rate on the y-axis. So I have to specify here, I want time, or you can put S here if you want, S and J1. So that should plot S on the x-axis and J1 on the y-axis. So let's see what happens. There you go. So this is sort of a hack way to plot. If you want to study the behavior of a rate law that you've got, you can use this trick, right? So where you use time basically as a proxy or as a way of, you're pretending that it's actually S. So I'm setting S to time, and as time moves, time is still moving forward in the background, right? So the model is still integrating in time, but I'm saying, well, whatever the time value is, I'm going to assume it, I'm going to set it equal to S as well. And I just plot S against 2. tends to J1. I could just do timing as well and actually get the same result, but it makes more sense to put S there. Okay. So now what else can I do here? Well, the other thing I can do is maybe I could look at the behavior of this graph as a function of Km. So maybe maybe I can do a range of Kms. So let's do a loop. Let's do a loop. Let's start a loop here. And we'll set Km to let's set it to 1, shall we, initially? And then after I've done the plot, I'll increment the Km by, let's say, 0.5, okay? So let's see what happens, shall we? Okay, so it's done 5 plots, all separate. You can see if you look at them closely, they do seem to change a bit, right, as I change the Km. But that's not exactly what I want. I'd like everything on the same plot. Now, in theory, our plot should let you do that, but I can't get it. I've never been able to get it to work. So instead, I'm going to use plotArray. And plotArray takes an argument, and the argument is going to be M. And what I can then do is show equals false. I think that's it. Let me just double check. I think it's show. Let me just double check with my other window here. Yeah. So what show equals false means is don't display the plot yet. Right now, each time it goes around, it'll actually use the same plot and overlay the simulations on top of every plot. So I should end up with one plot. The only thing I have to do, oh, there it goes. All right, there it is. Technically, I should do, oh, sorry. Technically, I should go plot array show equals true, okay? Oh, and it wants M there then, does it, I guess? And it'll plot it. Now, the other thing you might be thinking, yeah, hold on though. Be nice to have a legend because I don't know what's what here. Okay, so I'm going to stick in a legend, and I can stick in a legend but by putting labels equals. Then I can put whatever I want here, and that'll appear in the legend. So let's say if I just put KM. So now I have a legend, but it doesn't tell me what the value is. So let me just go add a string representing the KM. Okay, let's try that. Okay, that's better, but the colors are all the same. In fact, the other thing I want to do is I'm going to put an equals in here as well, make it look better. Okay, so we've got equals, but now the colors are not quite right. So there's a way to force it to use different colors, and that is reset color cycle equals false. Okay, so that means normally each time round it restarts the color cycle, and the color cycle starts at blue. But I'm going to tell it don't do that. Just pick the next color. All right. So if I do this, now I get all the colors. Okay. The other thing I can do is you might think that's a bit on the small side. And I think there's a, let me just see, let me just get the help from, okay, let me get the help from here. I think it's there should be a size there. Let me see if I can do it here. Fig size. Oops. Is that what it is? No. Can't remember now how to change the size of the figure.
Will it be in the help?
It wasn't there actually. But it takes any matplotlib argument. So let me just have a look here. Plot array. I got 2 screens here, so maybe fig size. It is fig size, right? Is the argument for matplotlib? I can't remember now. Anyway, you should be able to change the size of the plot and get it bigger. You can also, of course, with matplotlib, save these as PDF as well. At the moment, if I right-click on it, it just saves it as a PNG, which may not be useful for a paper or a poster or PowerPoint slide. but well, maybe for a PowerPoint slide, it's okay. But if you're doing a poster, you might want a higher resolution. You can use the matplotlib then to save it as a PDF. The other thing I can do is I can add labels here if you want. So ax label equals s, for example, and then if I do that, I get s down there. Okay, and I can put a y label as well. And I can set the scales to linear or log. I can put a grid on it, and I can set the x and y limits as well. And there should be, and if you don't like the legend slap on top of your nice plot, there's actually a argument outside equals true. And if I do that, so this is where I haven't demoed this, but it should okay. It tries to avoid the plot itself. Okay, the lines, so it doesn't cover the lines. All right, so this is very useful if you want to look at what a particular rate law looks like, and you want to see how different parameters affect it and so on. All right, so it's a bit of a trick you can use. So let's go back to the slides. Okay, that's the reversible, that's the plot array. We did that. Okay, so I just want to mention briefly, there's another way of doing quote unquote reversibility, which is to treat the product as a competitive inhibitor. And this is the equation you'd use. So you may not have the equilibrium constant, you may not have the you may not have the equilibrium constant, but you have the value for the product inhibition value, and you can use this as well as instead of the full reversible Michaelis-Menten curve. The idea of inhibitors, of course, brings up the idea of inhibition in general. This is a potentially confusing topic because there are so many different ways of doing it. This is for a single substrate, single product. This is the full potential for inhibitors. This figure you see here. So I is the inhibitor. So you can see the inhibitor can bind the free enzyme. The inhibitor could bind the enzyme substrate complex, and there are conversions between each of them. There are lots of possible ways that an inhibitor can affect the reaction rate, and these are given different names. They're pretty or bad names, I think. So I have a textbook, Enzyme Kinetics textbook, and this figure has come from that textbook. This tries to classify all the different kinds of inhibitions. So if you have the full possible mechanism, you can break it down into different kinds of inhibition. And these are what I mean by the words are really bad. I mean, you've got what's called uncompetitive, and you've got non-competitive. You have pure competitive, partial inhibition, uncompetitive, mixed uncompetitive, pure non-competitive, and so on. I'm not going to go through all this, but this chart shows you what each of the different inhibitors what are they called. All right, so competitive inhibition is where so this little figure here shows you that in competitive inhibition, the inhibitor binds to the free enzyme, but not the enzyme substrate complex. Basically, it binds to the active site and it competes with the substrate. Okay, so you get this kind of shape, and then you get other shapes depending on what part of the full mechanism is used. All the enzyme kinetics books talk about this. I'm not going to go into this now, but competitive inhibition is probably the one, probably a fairly common one you should know about. And so this is competitive inhibition, and each of these then generates a slightly different rate law. Okay, so each of these different kinds of inhibitors creates a different rate law. This is the rate law for pure competitive inhibition. Those of you who are fully alert may notice that this is the same form of equation for the product inhibition that you can use in a reversible Michaelis-Menten rate law. Okay, so the product basically acts as the competitive inhibitor. Okay, now you can do plots on these.
Is there anything you can do if the product and something else act as an inhibitor, or is it usually
just
if you're multiple that there's an inhibitor outweighs the product?
Well, in theory, that could happen. Yes, you could have E binding to one inhibitor and ES binding to a different inhibitor. Yeah, you could do that. And then you'll have to derive the rate laws yourself, because I'm not sure if anybody's done that. But
All
yeah,
right.
you could go to town on this and do all sorts of mechanisms. So yeah. It's just an example. I mean, some of those of you who've done enzyme kinetics will recognize the plot on the bottom left. This is a Lineweaver-Burke plot where we plot the initial rate, 1 over initial rate versus 1 over substrate. And for a competitive inhibitor, you get the straight lines. And a characteristic of a competitive inhibitor is it changes the slope of the Lineweaver-Burke plot. Basically, is changing the apparent Km, but the Vmax remains the same. Now, it's easy to see that if you do a log-log plot of the reaction rate versus the substrate concentration. So this is a log-log plot of the Michaelis-Menten curve, but at different values of competitive inhibitor. What the competitive inhibitor does, it basically moves the curve to the left, to the right, sorry, to the right. And what that does, it effectively moves the Km, the apparent Km, to the left. So as you add more and more inhibitor, the substrate Km appears to get bigger and bigger and bigger. But notice that all the curves reach the same maximum, which is the Vmax. So all that means is if you have enough substrate, you can always outcompete the inhibitor. And so you can always reach Vmax if you have enough substrate. So there are lots of ways of plotting these kinds of things. The Lineweaver-Burke is probably one of the most popular, but it's probably also the worst because of the way it distorts experimental data. This way, is another way that I've used log-log plots, but there are other ones as well that probably are better than Lineweaver-Burke. Although these days, if you want to do these kinds of plots, you'd probably use some kind of fitting software to do this. I mean, the reason for doing these plots is to try to estimate the KMs and the KIs and the Vmaxes. That's the whole reason for these plots. These linear plots were developed, when computers weren't around. It was easier to do linear, do straight lines with the ruler and so on, and then measure the slope and intercept by hand. That's the era they came from. Today, you'd use parameter fitting software to fit your data to the Michaelis-Menten curve. So. Okay, and that's just Michaelis-Menten, right? Now there's a whole bunch of other ones, because what I haven't mentioned are things like, well, sometimes you don't get hyperbolic kinetics, we get, sigmoid kinetics, and this is where the Hill-based kinetics come in. I'm not going to say too much on this, but you basically get sigmoidal kinetics. And if I go back to let's go back to the demo, because it's easy to change the model, so it does that. So this model here, if I want to make this a Hill equation, I just raise it to the power of the Hill coefficient, because I need, and then it's not Km anymore. I'm going to set it to N, and I'll set this to N. So I'm now going to study how the Hill coefficient affects the plot. So all I have to do is that in theory. There's a mistake. What did I do? Oh, okay. It really wants me to set up N. So this is a fail-safe. You have to initialize all parameters, is to protect you. And there you go. Okay. Maybe it's going too far. Let's take the simulation down to 5, let's say, instead. Okay, that's a bit better. Okay. So you can see here, when N is 1, we get the original Michaelis-Menten curve, which is this blue one here. And then when N is, oh, that's not working. Yeah, that should be N as well there. So let's rerun that. There you go. That's better. And it shouldn't be Km, it should be N as well. So now I can run that. Okay, that's better. So the blue here is what N is equal to 1. As I increase the Hill coefficient, it becomes more and more sigmoid. Okay. So you can see that quite easily there. All right. These are used frequently in gene regulatory models. Often transcription factors show cooperative behavior when they bind to the transcription factor binding site. And as a result, you'll get this sigmoid kind of behavior. So on the y-axis, it would be protein expression. On the x-axis, it would be some transcription factor. You'll often get sigmoid behavior like this. So that just shows the equation there. So it's very similar to the Michaelis-Menten equation, except that the substrate concentration is raised to the power of this Hill coefficient. I've done the demo. Okay. So that's the Hill base. They're pretty simple. If you want to do much more elaborate ones, you have the mono-Waymo changeur and the Koshland models. These were developed in the 1960s. These are to do with modeling allosteric effectors. So a lot of enzymes in metabolism are regulated by other small molecules, and these are called allosteric effectors. For example, phosphofructokinase in glycolysis is regulated by AMP. All right. So how do you incorporate those into your models? Well, you would use one of these MWC or KNF models. These are based on these models are based on the fact that proteins are multimers, they're made of multiple subunits, and the subunits can change state as an effector binds, and that can then result in regulation of the enzyme itself. So I'm not going to go much detail into this. There's two models. There's the concerted model, which is the mono-Waymo changeur model, and there's a sequential model, which is the Koshland model. Okay, so the only difference is that in the sequential model, the individual subunits change state one at a time. So the two states here, square and round, and in the sequential model, the states one subunit changes at a time. Okay, whereas in the concerted model, all states change at once, which to me seems more reasonable actually. And hemoglobin, for example, probably uses the concerted, operates on the concerted model, right? So hemoglobin will have two completely different states, where all the subunits are either in one state or the other state. And then what happens is ligands then can change the equilibrium between those states, and this is how you end up with cooperativity and allosteric behavior. Yeah, this is a very simple one. There are, this is the sort of full thing. You can make simpler versions of this or more complicated versions. This, for example, is a simple one. This is just a dimer, and I'm assuming that the square dimer doesn't bind ligand at all, and it's only the round one that binds ligand. If you work on this kind of thing and you try to derive the rate laws for this, you'll end up with something like this. Okay, and this looks something somewhat vaguely like the Hill equation, but you see there's a n here in the numerator and n minus 1 in the denominator. Sorry, n in the numerator. Sorry, n in the denominator and n minus 1 in the numerator. And there's also this L constant, which is basically the equilibrium between the two states. They can become really elaborate. This is just with n subunits. I'm going to switch over that, but you'll get, you'll get sigmoid behavior if you change the parameters. But they can get very elaborate here. So here now, I'm assuming both states can bind ligand, but maybe at different rates, and they start getting more and more complicated. And this then begs the question, well, what should I use? Okay, what should I use? If I'm building a model, what should I use? Well, first thing you should do is search the literature to see if anybody's derived the rate law for the particular enzyme you're interested in. If they have, use that. Okay. If you have no information whatsoever, you could probably get away with the basic Michaelis-Menten equation or even mass action kinetics. If you know it's regulated, however, and you know it's acting as an enzyme, there are these things called generalized enzyme kinetic laws, which I would briefly mention here. So these are things, there's two of them. There's the Honeycomb rate laws and there's the Liebermeister rate laws. Liebermeister rate laws are the most well-known ones. The Honeycomb rate laws are less known, but they're just as good, I think. They try to come up with a generalized rate law that you can use in all situations. All right, and they're extensible in the fact that you can have as many substrates and as many products as you want. You can have as many regulators as you want, and it basically builds them up in a block-like fashion to build up the rate law. So this is the generalized normal rate law. So this will take any number of substrates and any number of products. The substrates are alpha and the products are pi. And you can see that there's a product term here. So that's the number of products and substrates you have. All right. And so you can make this as big as you want. So for example, this is a uni-uni. This is a bi-bi. All right. So the bi-bi has two terms in the denominator and has two leading terms in the numerator. You can modify this to add to make it cooperative. So now you just add Hill coefficients to the powers and it'll become cooperative, such as this one here, uni by one. The other thing you can do is you can add inhibitors and activators, okay, by adding an extra term here in the denominator, all right? And you can either have inhibition or activation. Okay, so if you want more details on these, the paper for these honeycomb rate laws is here, and if you want to have this add effectors, there's the so this comp app bioscience was the old name for the bioinformatics journal. Okay, and they changed their name, but that's basically the bioinformatics journal. The other set are the Liebermeister rate laws. This was published in Bioinformatics in 2010. This really is very modular. In fact, this equation here is the full equation, and it has various components in it. The T, for example, is what's called a thermodynamic term, and refers to basically the mass action component of the rate law, and that's given by here. The ER is just the level of enzyme, it basically equates to the Vmax. Then you have D, which is the saturation term. So that's the normal numerator, the denominator you saw in the rate law, like Km plus S. Okay, that's that one. The D-reg is all about non-allosteric regulation. So that's things like competitive, non-competitive, uncompetitive inhibition. Okay. And finally, the R-reg, this one here, is all about allosteric regulation. So it's very modular. And you can put in as many of these components as you want, because each of them has a product term here. So the product term refers to, for example, how many allosteric regulators you have. These product terms appear refer to how many substrates and products you have, and so on. So it's very general. So if you're really stuck, you don't know what rate law to use, you can use one of these, and you can just build them up then as you add other components. Okay, so what we're going to do now is I'm going to set you loose on some exercises. So these exercises are going to be partly model building, and also more important is debugging. Okay, so if you've got mistakes in your model, how can you identify them and fix them? So we're going to have a couple of debugging exercises. So we're going to go to exercise 1 and 2 first. So let me just go over exercise 1 first. Are there maybe any questions first from anybody? I mean, we've gone through a lot of stuff here, right? So and we can have, little subsections where we can go over 10, 15 minutes, any particular topics as well. No problem.
We had
Yeah,
a couple
definitely
questions.
short break. Yeah, we can. Veronica says short break. Yes, and maybe we can go over some questions over as well. So
like the monodlyman or something like that.
Oh, worked example. Yeah. Yeah. Okay.
It doesn't have to be right now, obviously.
No.
And more curious than anything else. Someone else also asked about compartments. I have a little thing I could show about that if.
Yeah, that'd be good.
To.
Yeah, we should show compartments. Yeah.
Right.
Yeah, when you want to do that?
Can we do it right now, or do you want me to wait until?
Well, Veronica says that Veronica
break?
wants a break. Yeah, let's have a break. So how long do you want to break for, Veronica?
Maybe 10 minutes.
Okay.
Or 5 minutes.
Let's do 10 minutes. Let's do 10 minutes. So we'll be back at 20 past then. Okay, 20 past the hour. Everybody, time to grab tea, coffee, whatever.
All right, so this is just a little thing about compartments. So, so this is just a IPython notebook. I've installed tellurium, and that's it. So when you have compartments, the basic idea is that they can the only thing that's going to make it different is that if the compartments are different sizes, or if the compartments change size in time. Otherwise, it will behave basically exactly the same as a model without compartments. Because under the hood, even if you don't put in compartments, there is a default compartment of size 1 that everything gets put in. So here we have a reaction, just S1 goes to S2, but S1 is in cell, is in the compartment called cell, and S2 is in a compartment called mitochondria. And to make it different, the cell is large and the mitochondria is small. So if S1 starts at 10, that's a concentration in the cell, in a very large cell. And S2 starts at 0, and K1 is going to pump it into it. So can you, so here's my question. Can you figure out what's going to happen to the concentration of S2 in the mitochondria in this section? Normally, if everything was the same, like S1 would go down and S2 down from 10 to 0, and S2 would go up from 0 to 10. Anyone have a guess? So if I run this, yeah. So what happens is
concentration should be decreased, yeah?
The concentration should be decreased.
Of what? Which one? S1?
So will S1 be
S1.
So
No,
yeah, S1
it
will
should
go
be
down.
increased.
Yeah.
But does S2 go up a lot, or does S2 go up a little?
I guess S2 goes up a lot.
Yeah.
Because it has smaller
Volume, yeah.
Right, because S1 is basically an amount. When the reaction acts on it, it is not changing a concentration across that gradient. It is actually like moving molecules. So if we see this, S1 starts at 10 and goes down a little bit, and S2 goes up to over 400. And we can print the values here. And so S1 has gone down from 10 to 0.8, and S2 went up to 458. So that's just a little thing to show the sort of thing that happened. If they were both the same size, then we would get that, just as we would have expected. Similarly, if the first one was smaller, then the concentration would go up. The other thing I can show here is if we have time and just S1 and S2, do it this way. So you'll notice here, S1 has brackets around it and S2 has brackets around it. That means that we're showing the concentration of S1 and S2. So if I don't have the brackets in my selection thing, it'll plot the amounts. Oop,
Need a comma after 500.
Oh, right. Comma. There we go. So the amounts are actually like, so the same amount of S1 is leaving as S1 is coming in, as S2 is coming in.
Oh yeah, that's a good point.
But the concentration is very different because the total volume is different on the different sides of the thing. So that's a quick
do the one
summary.
with do the same thing, but with was it cell was 100 and mitochondria 2?
Yeah.
Just to show you the big difference.
Right. So with that,
I
guess the rates are different. Oh, the rates are different because the rate of K1 is based on.
Yeah, but you're plotting the amounts.
Yeah.
So the amounts change the same by the same.
Oh, right. Yeah, and the amount. So look at the amount. You'll notice starts at 1,000 now because we suddenly like changed the level of the cell from 10 to 100. So if the concentration is the same, the total number of molecules in that compartment is a lot higher than it was.
Yeah.
The other thing is that this value being used in the equation is typically is the concentration, and you have to say specifically if you want it to be the amount instead. And I won't go into that, but anyway. But basically, you have to know that like the value of like what your number means in the context of your model can change based on if it's a concentration or if it's an amount. And you can use either one. SBML will let you do either. Antimony lets you do either. But it can be a little tricky if you have to think things through as you do these things.
Yeah.
That's a quick
Okay.
summary.
That's good. That's good demo.
Sure.
Any questions on that?
Yes, one question. So the S1, and that's K1 multiplied by S1. The S1 is concentration right now.
Correct.
Okay.
And you can change.
When you're trying to figure out how to put S1 as
Yeah,
amount
like
there.
there's a way to say use S1 as an amount instead. And
I can't remember how to do that
what the
either.
thing is.
Yeah.
It's intuitive because kinetic rate should refer to the concentration either way.
Yeah. No, you're right. You're right. You're
It's
right.
important to
Yeah.
Right.
differentiate.
No, you're right. Yeah.
Thank you very much.
Okay, good.
Sure.
All right. Let's go and try the exercise then. So so let me just quickly go over the exercise. The exercise is basically to recreate this graph. Okay, that's all it is. Using this model. So the purpose of the exercise for you to see if you can interpret diagrams like this, put in the constants, and then run the simulation. So that's exercise 1A. So we can either go to breakouts or we can stay where we are. Well, what should we do?
Breakouts make it easier for people to ask questions, I feel.
Okay, in that case, then let me just briefly say what 1B is. And 1B then asks you what happens if you set the rate constants differently. And then don't look at the answers until you've done it all. And then see if you can answer these questions, okay? All right, let's go to the breakouts then. You did exercise 1, okay? So I've got the plot here for exercise 1. Let me just put some comments in here because I actually let me do this. And then we'll get rid of that. Okay. Oops, so comments in Python are different. Okay, so so this is the model, okay? This is the model. Those are the values we set up, and then I run that simulation, and I get the left hand one. Okay. Actually, this is the default was that, I think, wasn't it 20 in 1, if I remember right? So you got that, okay. And then we asked you what happens if I reduce it to 2. And one question I asked my group is, what does that do to the equilibrium constant? It does nothing because you're changing both rate constants by the same factor. So you're not disturbing the rate equilibrium constant, but you are speeding up the binding and unbinding. So if you do that, sorry, I'm slowing down the binding and unbinding. If you slow things down, you can see everything just slows down. In fact, the approximation is worse. You notice that S is doesn't stay constant here. Sorry, ES doesn't stay constant very, very long until it drops back down. Okay, so the original approximation we used for the Michaelis-Menten doesn't really easily apply here. And then we pushed it up to 2,100. That really does make the approximation really good. Now you see the ES level there is pretty much constant. Okay. The next question was, I'll get rid of that. Next question was, let's uncomment this, was how do I plot the flux or the reaction rate or the rate of product formation? Well, you have to name the reaction, then you have to use this selection list then to simulate that you want time in J2. And now if you do that, you just get P. All right. Then we went a bit crazy and said, well, you can compute anything you want really. And so here's the sine wave of product plus 2 using the colon equals here because we want to compute this continuously. And if I run this, I get a silly sine wave for P plus 2. Okay. Now the other one was exercise 2 was a debugging issue, I think. Yeah. So what I'm going to do is I'm going to take this, cut and paste this, right, and then paste it into here. Okay, and then I'm going to run a simulation. And then plot it. The question is what happens. So the question is what's going on there. Does anybody figure that out? I mean, it's actually going off to infinity. It'll just keep going on and on and on. What's the problem there? Anybody figure that out? Okay, the thing to look at is this rate here, K1 times S1, is actually a fixed rate. Because K1 is a constant, and actually S1 is a constant as well, because it's a boundary species, and it's constant at 10. So the rate here is 0.1 times 10, so it's 1. So the rate through here is 1. Okay. What's the rate through here? Well, the rate through here is governed by the Vmax. The maximum rate that can go through here is Vmax, and the Vmax rate is 0.5. Hence, 1 is greater than 0.5. So S2 will just accumulate forever, and it's not possible for the second step to run fast enough to absorb the change in S1, or S2 rather. Okay, if I were to set the Vmax to 1.1, which is slightly higher than 1, it still doesn't work, because that should work actually. Let me push it up to 50,000. Oh, sorry, yeah, no. 0.1 times 10. Yeah, it is 1. Yeah, why is it? Let me push it up a bit more then. Oops. Oh, I know, because okay, this is something you got to watch with Jupyter Notebooks, and it gets me every now and then. The reason this wasn't working was because I forgot to run the model cell. All right. This is one reason. Yeah, this is something you got to really watch with Jupyter Notebooks, because you have lots and lots of cells up here. If you're running a particular cell lower down that depends on upper cell, you got to make sure those are up to date. Okay. In this case, it wasn't. So let me run that now, and then run that. Now it's better. Okay. In fact, it's gone a bit too crazy now. And I don't know why it does that step there. What's going on there? Did I get that right? Oh, there, that's better. Okay. So now it's actually leveling off and it'll reach a steady state. There are things here that let you execute all cells, I presume. What's the trick for executing all cells?
Yeah, run all.
Oh, run all.
Yeah.
If you're not sure, you can just run all, right? And it'll run every cell. And now that may not be what you want to do, but that's one way to do it if you can't remember. So be careful with that. You get some very subtle bugs that way. Okay, so that's the problem there. Okay, that explains what's going on there. What's wrong with this one? Let's run this one. Also, something goes off to infinity. What's the problem there? Anybody? So S2 is
The
going
K2 should have subtract words.
Yeah, it should. Yeah. What's happening here is that the S2 to S3 rate is now fixed. It's not a function of S2. So now if I do that, I get much more normal. Sometimes these bugs are very difficult to spot, especially if the model is really big. And in fact, we've submitted a grant to try to build a suite of tools that'll let you check a model for lots of different kinds of mistakes. All right, so you can get a report back to make sure that for big models it's an issue. For little models, you can probably figure it out, but for big models like with 100, 200 steps, it becomes, and with the rate loads are complicated, it can become difficult to spot the problems. Yeah, there it goes. I missed out the S2, and I think that's it. What's this one? Oh yeah,
S1 in line 3.
Yes, thank you. So that was an easy typo you may have made. You didn't mean K1 times S1. You actually meant S3. Okay. Now we had an interesting thing that happened in our session, which I want to show. Let me take that out. So by mistake, it's an easy mistake to make. Somebody left out the E in the first reaction. Okay. Now this meant that the reaction was independent of E. And so even though the rate may be, even though there's no E, the rate could still be positive, which meant we're using up E, even though there's no E. That would result in negative concentrations, right? So whenever you see negative concentrations, there's something funny going on in your model. It's usually a bug somewhere, okay? In this case, forgot to put the E in, all right? This is called a zero order error. So if I put the E back in, it'll work fine.
What if I wrote K1 times E plus K1 times S?
Let me see what. Oops, sorry.
It's capital K. There you go.
Yeah.
Same problem.
Same problem, yeah. That's because the second term is dominating them. And
yes, right.
Yeah.
Makes sense.
Yeah, makes sense. Yeah. Anyway, these bugs are easy to miss, easy to miss your little fingers, type the wrong thing or whatever, or you forget something. Easy to do that. Whenever you get negative concentrations or things going to infinity, you've got a problem with the model. Okay. So then you got to try and track it down. All right. There you go. And that one should be S3. And that's it. All right. So we got 4 minutes to go. So I have a couple of new topics. I'm not sure we should do because Joe Hellerstein is going to come on, I presume. Is Joe here?
Yeah, I'm here.
Oh, good. So I can cover this another time. But basically we're going to cover things like steady state, which is pretty straightforward, and applying perturbations, and doing some and solving ODEs and things like that. Let me cover that another time. We'll find some time in the next few days, but because I don't want to.
There'll be some extra time in the afternoon on Thursday. So.
Oh, okay, great. We can do it then. Yeah, no problem. Okay. All right. So the last 3 minutes. Any final questions? And don't forget, if you have any specific topics you want to go over, we can do 5-10 minute sessions even after the afternoon, for example, right? Although this stops at noon, right? If there's something short you want to go over, we could spend a few minutes doing that after noon my time. So. Or if you have, models of yourself that you're having problems with, you can ask us about those too. Okay. Looks like there's no.
In a situation where, for example, I work with CompuCell and I have, for example, a cell defined in a region.
Yep.
How could I import this region into Tellurium, or vice versa?
So that's possible. You'll learn about that in if you do the CompuCell course coming up. They'll go over that. In fact, James Glazier may mention it on Friday. Yeah, we worked with CompuCell 3D to let you do that. Same goes for PhysiCell. So you can load in a Roadrunner model. It's basically Roadrunner. You can load in a Roadrunner model into every cell in your model. And you can even have different models in different cells. And then you can wire up these cells as well, depending on what your network is doing inside the cell. So yeah, that's perfectly possible. But you'll hear about that Friday, I think. And if you do the course, you'll hear a lot more about that.
Is it possible to have a bit of back and forth between something like CompuCell and PhysiCell and Tellurium, so that you can import your chemical species and have cell uptake?
That's a good question. I think you can, yeah, because they have external fields which are outside the cells, and I got a feeling you must be able to have a transporter to transport them in. You'll have to ask them that, but I wouldn't be surprised if you can't do that, because that would be an obvious thing you want to do.
Yes, this I know you can do.
Oh, you can. Okay, good.
Yes.
Yeah, they have external fields, so you can. Yeah, all right.
Okay, awesome.
Yeah,
Thank you.
Yeah, great. All right, well, we've reached the top of the hour.